Alright, so I was asked to do maybe an example from chapter 11, the power series stuff. Um, so we have this differential equation, and the instructions are to find a power series solution, find the radius of convergence, and to identify that as an elementary function. Um, so actually, maybe, even though I don't really have to do this, maybe let me solve this in another way first, because this is a separable differential equation. Like if I just write y prime as dy over dx and I move some stuff around, I get this. So I get this. So I get that. And then I can solve it for y. So I would do like, yeah, okay. So absolute value of y is e to the x cubed over 3 plus c. And then here's what I can do. I can take the absolute values off. That's going to make this a plus or minus. But what I can really do, I can take this e to the c, which is just a constant, and then there's also plus or minus, which I can just say now c prime is a constant that might be positive or negative. So I can say that this is the general solution. Which this isn't a power series, but this will help us. Okay, so let's actually do the problem now. Find a power series solution. We assume y has a power series representation like this. I want to plug this into a differential equation. This involves the first derivative, so I need the first derivative, but that's it. Remember, this starts at n equals 1. Like that. So let me plug this in. So I put y there and y prime there. And now I want to, right, I would like to, basically what I would like to do is I would like to equate coefficients on each side. On this side, we have this series that has, for example, an x to the 0 term, an x to the 1 term, an x to the 2 term. So the coefficient of each power of x on this side should equal the same thing as the corresponding power of x on this side. I would like to simplify both sides so it's clear what the coefficient of a specific power of x really is. So maybe the first thing I would like to do is take this x squared inside. So it's now cn x to the n plus 2. And now I would like to match up this with this. I typically like to make the powers of x really look the same. So actually, yeah, here's what we'll do. I want the power of x to just be n. I want both of these to just have an x to the n in them. That means I would have to bump this by 1, and I would have to bump this down by 2. But we can do that. This is re-indexing the sum. So if I need this n to be bumped up by 1, what I do is I bump down the indices by 1. So now n will go from 0 to infinity, and all of these n's get replaced with n plus 1s, including this one, so this n minus 1 just becomes an n. So this is now c sub n plus 1 times n plus 1 times x to the n. I can also bump this. I would like to replace this n with an n minus 2, so that way this n plus 2 just becomes an n. So I'm bumping these n's down by 2, so I should bump these up by 2. Like that. So, right. So this tells us this coefficient has to equal this coefficient. But let me be careful here because this sum only starts at n equals 2 and this one starts at n equals 0. So like, yeah, so what I just wrote is valid as long as n is at least 2. But what about when n equals 1? When n equals 1, like the x coefficient here would be c, like 2c sub 2. The x coefficient here would be 0 because we just don't have an n equals 1 term. So c2 is 0. There's also the n equals 0 term. I'm just focusing on the terms that exist on this side, but they don't exist on this side. So the n equals 0 term would be c1 on this side, and it would be 0 again, because that term is missing on this side. This doesn't have an n equals 0. So c1 is 0. So let's now try to talk about this recurrence. Yeah, because so now this so C1 is 0, C2 is 0. We don't know what C3 is. Or actually, it's true that I don't know what C3 is. I also don't know what C0 is. Yeah, I forgot this starts at 0. The first coefficient is C0. So so that's the first one that we don't know. I think we can figure out C3 in terms of C0, though, using this rule. So like, yeah, so C sub n plus 1 is C, so this should be, right, sorry, let me write the rule. I'm being a bit disorganized here. C sub n plus 1 equals C sub n minus 2 over n plus 1. That's the rule I'm using here. So C sub 3, this is like if I'm putting in 2 for n, so that should be C0 over 3. So let's talk about C4. For C4, I'm putting in 3 for n, so that should be C1 over n plus 1, but C1 is 0. Let me show my work there. It's C1 over 4, which is 0. C5, using this formula with n equals 4, this should be C2 over 5. Oops. Yeah, I'm really messing this up, aren't I? No, yeah, I'm fine. Just a little bit scatterbrained here. Yeah, C5, n would be 4. I plug that in, I get C2 over 5, which would be 0. Yeah, so, okay, so what is this pattern? C0 is just whatever it is, and then C1 is 0, C2 is 0, C3 is this, which is not necessarily 0, and then C4 and C5 were both 0. C6 is going to be C3 divided by 6, which in turn is C0 over 3 times 6, right? And then there's going to be a pattern that continues, right? This gives me a formula for a particular coefficient in terms of the coefficient like that's 3 before it. Like n plus 1 to n minus 2, that's a gap of 3. For example, when I did C5, this was in terms of C2, like the coefficient 3, like the subscript is 3 below this one. So what we're going to see is we're going to see 2 zeros and then a non-zero, and then 2 more zeros and then a non-zero, right? And that's how it started from the beginning. The C0 was not necessarily 0. It's just whatever it is. And then the next 2 were 0. And then C3 is this, which is not necessarily 0. And then the next 2 were 0. What we're going to see, so C7 and C8 are both going to be 0. C9 is going to be C6 divided by 9, which is C0 divided by 3 times 6 times 9. C10, C11 would be 0. C12 would be C9 over 12, which if I put in what C9 is, that would be C0 over 3 times 6 times 9 times 12. So maybe now we're starting to get the pattern. Of course, this goes, there's the 2 zeros and then a non-zero, and then a 2 zeros and then a non-zero. The most important thing now is to figure out the pattern of the non-zeros. So we had C0 over 3, or maybe I should start it just plain C0. The next one was C0 over 3. The one after that was C0 over 3 times 6. The one after that was C0 over 3 times 6 times 9. And then this one. So why don't we say C sub 3m, if m is a multiple of 3, it seems to be C0 over 3 times 6 times 9, all the way up to 3m. Like for C sub 12, we multiplied all these multiples of 3 up to 12. And we can simplify that. That's C0 over, if I pull out a big power of 3, because I can pull 3 out of this, 3 out of this, 3 out of this, and there's m things. So if I pull a 3 out of each one, I would have 3 to the m. And then what's left would be 1 times 2 times all the way up to m. And we have a name for that. That's m factorial. So we have that. So, right, where are we now? I would say that we found our power series solution. Basically, right, our coefficient is, for all the subscripts that aren't a multiple of 3, like C sub 1, C sub 4, C sub 5, all the subscripts that aren't a multiple of 3, those are 0. If it is a multiple of 3, the coefficient is this. So, right, it's this, but once again, we can focus only on the multiples of 3. So let me index this by m. And I will just put in what happens when, so basically n is 3m. So I'm going to put C sub 3m x to the 3n. Oops, 3m. Right. And so that's our power series solution. Let's find the radius of convergence. To do this, we do the limit as m goes to infinity. I will do the m plus 1th term over the mth term. Be careful here. This is not just 3 times m plus 1, like you, well, it is, but you want to use the parentheses. Yeah, and as usual, I flip the bottom. And then there's going to be a bunch of stuff that cancels. So like this cancels this and leaves just a 3. M factorial and m plus 1 factorial, if you're comfortable with this, this cancels and just leaves an m plus 1, because m plus 1 factorial is m plus 1 times m minus 1. And you can cancel everything except the m plus 1 with this. C naught cancels, and a power of x cancels. I just have x cubed. So almost everything just went away. What do I have here? X cubed over 3 times m plus 1. And as m goes to infinity, this just goes to 0, no matter what x is, because m is in the bottom. So what are we doing here? We're doing the ratio test, and if we got 0, the series is convergent as long as you get something less than 1. So this converges regardless of x. Sometimes you get a meaningful inequality that you have to actually solve for x here. So sometimes this limit actually does depend on x, but in our case it was 0 no matter what. if it wasn't 0, if it was something that depended on x, then I would just set that less than 1 and solve for the values of x that that satisfy that. And that's how you would get the radius of convergence. Is just the radius of convergence is half the length of the interval. You get the interval by solving for x. Oh, so yeah, maybe I should make sure to answer the question. So for us, our radius of convergence is infinity because it converges for all x. One last thing, we should identify this as an elementary function. Of course, this is where it's really going to help. I mean, we basically already identified it as an elementary function, but we should make sure to like justify this with the answer that we got here. So, but this is where it's helpful because we know exactly where we're going. I know that y is this. Let me make this look a little bit better by pulling the C naught out. And I can even, so let me show you. Yep, here's our old friends. Here's e to the x. I know this is relevant because I already know that we're going to have an exponential function. So I'm definitely looking at e to the x. E to the x is this. What I have is this. This has an n factorial in the bottom and an x to the n. Let me make this look a little bit better. About this 3m in the bottom, this is bothering me because there's no 3 to the m anywhere in here. But I can take this and put it with the x like that, because this is like x cubed to the m and this is like 3 to the m. And now this is looking a lot more familiar. This is exactly like this, except I have m's instead of n's, and instead of just plain x, I have x cubed over 3. So this is not e to the x, this is e to the x cubed over 3. So the solution I got is a constant, c naught could be anything, times x cubed over 3. And just like I said it was at the beginning. Anyway, so let me make a moral of the story here. Obviously, this problem is a long problem. I'm unlikely to ask you to do a whole thing like this from beginning to end with all 3 of these sub-questions on the final. In my mind, first of all, the fact that we were able to even solve this one from the beginning using another method, to me, that is kind of not the best example of power series, because the real use of power series is for when the solution isn't an elementary function. Because if it has an elementary solution, then we would already know how to do it before chapter 11. In my mind, the important part is getting to about here. Like the work that we did to start with y as a power series and do this manipulation where I plug in y and y prime, and I do this work to get the powers of x to line up, and then I write that this coefficient equals this coefficient. This is all just to derive this, which is this is the recurrence relation. In my mind, deriving the recurrence relation is the most important part. So if I'm asking you a question out of chapter 11, that is most likely what I'm going to pick on. I might really ask you about a radius of convergence or something like that, but deriving the recurrence is the most important part. After deriving the recurrence, then we started all of this business where it was trying to find the pattern, but all of that was because we were trying to recognize this as an elementary function. So yeah, if you have to pick something out of this to really focus on, I would focus on like the work we did up to here.